Just give me 1 minute. Okay. So for now, he said, so we can just join.
I know, I met him.
Okay. Oh, you already spoke to him.
I already spoke.
So let's start. So today we have Anirban from Seoul National University, and today is his colloquium, and tomorrow he's going to give the seminar. He did his PhD from the Tata Institute of Fundamental Research under supervision of Vasudev, and then after that he moved to SLAC, and in 2020 as a postdoc, and this is his first, this is his second postdoc. And he's going to talk about neutrinos, the key to dark sector in this colloquium. So,
thank you very much, Viraj, for the introduction, and thank you to everyone for coming. So this is a colloquium. So I'm trying to be in my slides. I'll try to be as simple and as approachable to all of you as possible. And also, I will emphasize that please feel free to stop me anytime if you have any questions. Okay, so neutrinos, they are special. So they are part of the standard model. We have 6 quarks and 6 leptons, but unlike their fermionic or even the charged electronic counterparts, I think I should point to the here because okay. No, I was thinking about the people on Zoom if they are able to see my point. This way, and probably.
No. Okay. Have people joined in Zoom, or are there any people? Can you just check? Sorry, just see if this is what.
There's only one, so I don't know.
No, this is media, so nobody is there in Zoom. Oh, top. Is this top of the screen? No, it says participants too.
We can see.
So one is media and one is here.
Okay, so I don't need to point.
Yeah, so you can just use the.
Okay. Okay. So as I was saying, even from they're very different from their charged electronic causes. They're very light. They don't have any other interaction other than the weak interaction, so which is very weak, very understandable. So they arise in the theory as to momentum or energy mismatch in the beta decay. In the 30s, it was proposed by none other than Wolfgang Pauli. And for a long time, it was thought that neutrinos will probably never get detected at all in laboratory because they have so feeble interaction. But finally, in 1950s, Huon and Reines, they did an experiment which is called polaric-poltergeist, and they saw neutrinos from the sun, from a nearby nuclear reactor, and you can see here in this photograph both of them with that of this polaric-poltergeist, and that was in 1956. But today we have come a long way from then. And now combining all the experiments on different parts of the world, nowadays we have a percent level precision of different parameters of neutrinos, their mass difference, their mixing angles, and so it basically shows that we have learned a lot about neutrinos in the last 70, 80 years, and but still there are many questions. So this is here shows the mass spectrum of all the particles in the standard model. Here we have the quarks and the leptons. You can see the lightest one is the electron here, and it's roughly around MeV, mega electron volt. But neutrinos are all the way down here. So there is a mismatch. There is a gap of the order of 6 orders of magnitude. And we don't know why this gap is, what's causing this gap. It looks, just looking at this parameter space, it looks very unnatural. Not only that, we don't know what the neutrino mass is. So it's like it has
very high question. Sorry. So when you say that why there is such a gap or something like that, doesn't it theory says that at every scale you should have particles, or when you say that there's a gap is something unnatural, why do you say it is unnatural?
Yeah,
particle at different scale, and there can be gaps as well.
Yeah, but I mean, it's an like theoretical expectation of us to, if there is such a gap of many orders of magnitude, there must be a reason. There must be an
there's some symmetry argument or something like that. It's what we
so people have tried to explain this gap, and they have used symmetries, higher order symmetry or high energy symmetries, which get broken, and then you get this mass gap between the charged electrons and the neutrinos. So it's more like a theoretical question, or we just want the answer to is why there is such a gap. And I mean, you could just say that of course there is another theory of just having a very weak U-Kawa interaction of between neutrinos and Higgs. So then also you can explain this light mass. But then the coupling, then you might ask then why the coupling is very small. So yeah, you could call them it's just our theoretical questions, or what's I don't what's the right word, but anyway, I mean, what I'm trying to say is that it's mostly from the theoretical point of view. We want to understand why is this such a big difference between these two masses of neutrino and the other components of standard model.
Okay, but it is not such a something like a significant kind of thing, like a cosmological constant.
No.
Problem, not a problem as such like that in the order of magnitude difference or something.
No, of course not. It's not like there is no fundamental reason for them to be same or something, same order of magnitude.
To have particles in every decades of energy.
Yeah. So it's not like that. Yeah, it's not a tension or anything. But it's just our theoretical curiosity, you could say. Yeah.
In the electronic sector, the mass matrix has large angles, so it's not like the strong sector.
Yeah. So in the electronics, the neutrinos have very large off-diagonal mixing between different mass bases, mass states. So yeah, that's a. You mean in the context of some UV model where leptons and quark belong to the same?
Of course, quark sector also there is like
yeah,
within a doublet also.
Yeah, exactly.
Except with the highest.
Right. Yeah. Compared to the quark doublets, lepton doublets, there's a you could say that there's a mass difference, quite a large. So yeah, in a sense, so I have not done much model building or UV completion of standard model, but I know there are some grand unified theories where actually you can form multiplates with all quarks and leptons.
This kind of issue will not be a problem.
As far as I know, you still have to you still have to explain the neutrino mass with some right-handed neutrinos and small coupling. But yeah, so in that sense, I think that problem still persists. They're in higher symmetry theory.
No. So usually if you have a electroquark theory, usually people assume quark electron universally. But here the most no, I'm talking about the universality of the weak interactions. In the weak interactions, they treat the quarks and electrons as universal interactions. Differentiate in the weak sector between quarks and electrons. But then if the equilibrium is maintained in the electron sector is so large order, I was wondering whether it has some implications for the electroquark theory, some of your sense.
It would also run some mixing and
That they want us to do.
Yes, so yeah, it's not a given thing. So I think you still need some special mechanism to explain that, even above standard model or beyond standard model. So yeah, so there are these lingering questions. Some of them are very much theoretical, university again. So we don't know how they get mass, why they're so light, and what are their actual properties and interactions. We know that they have weak interaction and they're leptons, but what if they have something more than that? Whether they are coupled to the dark sector, and that's a plausible thing because the neutrino mass, as I said, neutrino mass is not explained within the standard model. You need some beyond standard model theory to explain that. And that already tells you that there is something neutrino has to or might be talking to some other sector, some other new particles for its mass mechanism. So it's a quite natural thing to ask whether it's already, we know that the dark sector is there in the universe, and whether there is a connection between these two sectors. As some part of the first part of this talk will be related to the cosmology and neutrinos in cosmology. So let's look at the cosmic timeline and when the neutrinos become important. Some of these processes, some of these events are beyond standard model, or some in the standards that we are happening in the standard model. So if you start from very high energy and high scale, there is a seesaw mechanism mass scale, which I was mentioning before for Dhiraj's question, is a very popular model which gives very light mass to neutrinos. And this roughly 10 to 11, 10 to 13 GeV is a very important scale for that. Then there are models of sterile neutrinos. So sterile neutrino is basically, and so in the standard model we have 3 flavors of neutrino, right? But there are again some theoretical explorations which say that there could be more. There could be 1, 2, or 3 more states of neutrinos. And those are called sterile because they don't have a very strong interaction with the other parts of the standard model. So there are some models where you could produce these sterile neutrino at around 10 scales of GeV, and you could actually have the sterile neutrino as the dark matter in today's universe. So that's a very popular model, and it's a very active field of research, and a lot of work has been done. Is being done. on this model. Then in a if you just look at the active neutrinos in a standard model, they were coupled all the way until billion, roughly temperature of NEP. And after that, they decoupled from the bath, from the thermal bath, from the bath of photons and baryons. And then they start free streaming. And around temperature keV, neutrinos become neutrinos. Some of these rare neutrinos can become start becoming non-relativistic. So that also has some implications in our cosmology, which I'll discuss later. And finally, in the EV scale, in the CMB power spectrum, these neutrinos can have some effects also. This part I'll explain in more detail in a minute. And finally, at the very late time, these massive neutrinos, they have some, they can also suppress structure formation at small scales because of their large velocity and free streaming. So these are the few different points in cosmic timeline when neutrinos become important. There could be more, of course, but these are the some of the most popular ones. And in today's talk, I'll focus on these three time epochs. So I'll first explain what's happening in CMB, and then I'll come to the very late time some of the observations involving neutrino and dark matter, and then I'll briefly talk about a general theory of warm dark matter. So, so these are the main two parts of this talk. The first one will be I'll be asking what if neutrinos have some extra self-interaction more than the weak interaction, more than the standard model interaction that we know, and what are the effects of that in CMB and in present day universe. And the second part, I'll ask the question of dark matter neutrino connection, if there is any such connection, and what is the results of that. Now, this is so I'll have to explain what CMB is. So CMB stands for cosmic microwave background. So this is a picture of our universe actually, when it was around 330,000 years old. The temperature around this time was roughly EV or 0.1 EV, and this was taken by one of the experiments called Planck, which had observed this CMB sky in the whole universe in all directions. And this color map that you see are the temperature fluctuations in the photon. So so at this wavelength, so this is in the microwave wavelength right now, but at this wavelength, the temperature or the intensity of photons are more or less synonymous. So you can just call the temperature or it basically says how many photons are coming from that direction. And these fluctuations are of the order of 10 to the minus 5. So these are very, very tiny fluctuations. And so if you zoom out of this picture, you'll just see a very uniform sphere, which basically says that the universe was very, very homogeneous and isotropic at early time. Now you can ask, why are these fluctuations coming here? Now, the reason behind this is acoustic oscillation in the photon and baryon thermal bath. So in the high temperature, when the universe was younger than CMB age, the photons and baryons were coupled together because of their electromagnetic interaction, and that creates a thermal pressure, which kind of pushes the matter away always, creates an outward force. But there is also gravity. So gravity is always trying to pull two different parts of the universe of our matter fluctuations. Gravity is trying to pull them together, and because of this tug of war, it creates ripples in the universe. It's much like the ripples we see on the surface of a pond. So because of these two forces, there is this constant oscillation or acoustic oscillations, basically sound waves in this thermal bath. And these fluctuations are basically the total picture that we see because of these oscillations. Now, this map has been a treasure trove for us. We have learned so much about the universe just from this CME map. So one of the way we learn physics about the early universe is this 2-point function. So you take 2 different directions, you look at the CME map in 2 different directions, and then you measure this small temperature fluctuation. So temperature difference from the background temperature, from the uniform background temperature. You take those deltas, delta t's, and you compute the 2-point function. So of course that would be a function of theta, the angle between these 2 directions, and that gives you the 2-point function. And then you take the angular Fourier transform and you go to the multiple space on these L's. So the L's are basically spherical harmonics, just the same L, the angular multiple. And we get this plot, this nice plot. So the x-axis here is the angular scale for ease of our understanding, and this is the multiples, and the magnitude or the y-axis here basically tells how correlated these 2 points are at 2 different angular scales. So you see there are many, of course, there are these oscillations which are basically coming from this baryon acoustic, the acoustic oscillations in the photon thermal bath. And of course, this is not an uniform oscillation. The amplitude of the oscillation is dying down. So we can actually learn very different things. I mean, learning this whole spectrum can give you it deserves its own course or own seminar altogether. But some of the few things that we can learn is just from the position of this first peak, we can tell how much dark energy is and how much dark matter is, how much baryon is in our universe. Similarly, the height of this secondary peaks, the second, third, and fourth peak, they also tell us how much dark matter and how much baryon is there. And the decay rate of these higher peaks, they tell us the shift damping. So it's basically saying is that if you go to very, very small angular scales, the photon is not very exactly coupled. Sorry. Yeah. Yeah. Right. Yeah. So your question is why we see this at 1 degree? Right. Yeah. So that's. Yeah. Right. So that depends on. So that depends on how fast these sound waves. So you have this thermal bath of photons and baryons coupled together, and there are sound waves in this plasma. And this 1 degree scale, that depends on how fast the sound waves could travel from the beginning to the edge of the CMB. And if you compute that, you would find that the corresponding length scale corresponds to 1 degree. It just depends on how much baryon is there, how much photon is there, and what was the age of the universe at that time. So that gives you it's basically size of technically it's called size of the sound horizon. So that's how far the sound might have traveled at that time. That gives you the 1 degree scale in your plot. Right. Yeah. So there is a very nice reason why the errors are large. It's because so these are big angles, 90 degree, which is already quite big. So there are not many different observations you can make with these large angles. So this is called the cosmic variance. It is called cosmic variance because with larger angles you don't have much statistical much statistical strength in your observation. So that's why the error bars get big. But part of it is also coming from the experimental or technical limitations, how much you can measure.
Sorry, there is, so for Planck in temperature, there is no technical limitation. The best we can give.
Yeah.
It bases on two things. One is what you said, cosmic variance.
Yeah.
So the thing is that for every L, you have this, because you decompose it in this YLN, right?
Yeah.
Spherical harmonics. For every L, there are only 2L plus 1 M modes.
Right.
So
Yeah.
that is what, as you correctly said, and there is also the F sky, how much the sky coverage that Planck already did the best one can do even in 100 or 200.
Right, right.
So 80% sky coverage probably around that point, or 70% by cutting off all galaxy.
Yeah.
So there is, even if there are hundreds in the experiments, we cannot 2 to 10 or 2 to 100, we will not be able to make it better than that.
Yeah.
So the only explanation is twice M plus 1, twice L plus 1.
Yeah. So yeah, exactly. So in this case, in case of the Planck experiment, I don't remember if you mentioned this data is from the Planck experiment by European Space Agency. For them, the cosmic variance is the limit, but there are also other experiments which they actually try to look for lower angular scales. I mean smaller angular scales, and for them they don't actually go to very large angles. But anyway, yeah. So here it is, the error bars are big because of cosmic variance. So as Tejas mentioned, for each L we have only 2L plus 1 modes. So that kind of goes down. So we don't have many observations for large angles. So you mean why it's kind of going down here? Sorry. Right. Yeah. So it's probably not the best way to show the error here. Still damping is the whole thing. It's not only it might look like the silk damping is only from this point, but it's actually the whole thing. But the reason behind why there is a the second peak and third peak almost have the same height is because because of the baryonic loading. Or if you just look at if you take the CMB physics and take the very simple model that there are some baryon and they have some thermal pressure because of photon interaction with photons, and they are oscillating, you would expect that that all these peaks would have the same height. But then you also add the mass of the baryons or the amount of baryon, and that kind of I can go quickly. So the oscillations would be symmetric about the 0 point. And in the power spectrum, we are actually measuring the positive part. The oscillations in the baryonic baryons and photon thermal bath, these are just sound waves. So yeah, in a 2-point function, you just invert the negative part, and you see that all of these peaks they should have the same peak heights. But there is also baryon, and they have some mass, some finite mass. So what happens is that the 0 point, instead of being it here, it actually comes down. It looks something like this. So then what happens? Then you take the positive of this, and now you have an asymmetric pattern in the oscillation. So that's what is happening here. So your odd peaks are higher than the even peaks, and this asymmetry in the peak height just also tells us how much baryon and how much dark matter there is in the universe. Yeah. That's what is creating the asymmetry. So that's basically, so it's like if you look at the spring problem, right? A mass connected to a spring, and the spring is connected to some rigid point here, and you will have some normal oscillation. Now, if you rotate the system and let the gravity also act on it, then you will see that the 0 point, which was here when it was oscillating horizontally, now the 0 point is moved down. So it's actually oscillating around a new reference point. So it's very much like that. So now you have the baryons, which has some mass, and that's also, they are already trying for the fluctuations to come together and sets a new 0 point, a new reference point of the oscillation, and that creates the asymmetry.
But why won't something work for any two consecutive peaks? It should have worked for any two consecutive peaks.
It does. So if you didn't have self damping, all of this peak would be roughly at the same level, and you would see that the first peak is much higher than the second peak. Third peak is again much higher than the second peak. So all odd peaks will have higher heights than the even peaks. So and that's actually happening, but it's not very apparent because of the self damping, because of the diffusion of photons at very small angular scales. That is kind of suppressing the higher peaks, all of these higher peaks to lower levels. So you can't really see that, but you can still see that if you come like this, second peak should be somewhere here, right? But it's not here, it's actually here. So yeah, so third peak is actually much stronger than the second peak. Does that answer your question? Yeah. Okay, so now we kind of understand at least some, yeah. By azimuthal direction, you mean?
The 2 point function in that depends on the theta.
Yeah.
Does it depends on theta and phi?
Right. Yeah. So so there is okay. So you mean the azimuthal direction? Right. Yes. There is of course but when we calculate this 2 point function or this CLs here, we average over all the M modes. Average over all the M modes. So there are like for each L there are 12 plus 1 number of M modes. So we kind of take average over that, and then we are left with only the L's or the.
Is there any information that you can get this stage by function? So you talk about multiple.
Then we have a only answer.
So what happens is that muscles you have non-Gaussian, so bispectrum. So that so Planck has found the bispectrum. So what happens is that the Gauss spectrum has a reasonable error curve. Anyway, we go for 3 point function, error curve per single. So even in that case, we have pretty good understanding of this bispectrum. What we found that the non-Gaussian parameter, the departure from Gaussian fluctuation is nearly 0. It is I think 2 plus minus 5 or something like that, or 2 plus minus 4. So we are consistent with 0. However, this is for a particular template of non-Gaussian. So for different template, the estimation changes. So what happens is that people are thinking of future observation of the where you can reduce the error cost at smaller intermediate scale where they can outperform that and can have more function. So that is the status. As of now, with bispectrum, we have been able to rule out some models, but we have not been able to get any fundamental. We have not been able to make any fundamental.
Right. Yeah. And I have read, yeah, kind of like that.
And then you are assuming that the file is in the I mean, rotation stuff like that. Now, that is pretty right near rotating. And assuming that these two angles and all points have similar difference.
He is just integrating over 5 and giving him a 5. By the way, this theta is not necessarily the theta of spherical program.
Oh yeah, it's just
You see the theta between two different directions. Not one of these directions has to be aligned with the other.
Yeah, that's what I was saying. That is and
Yeah, but you can orient one direction, even one direction. You integrate out, then you set up a new Z direction. So this is all integrated.
Everybody is asking whether we are basically, when we are doing this summation, whether it is allowed. Yes, that is. Yeah, the thing is that you can do that if there is this statistical isotropy. There are some words on statistical anisotropy. Actually, there is a angle of reference where along a particular axis, the CMB map looks a bit different. There is a 3 sigma to 4 sigma. If you have heard, Tarun sort of talks talked 2 weeks ago. Yeah, but it is there in this thing. So there are works on that. So it can be a statistical thing, or it can be some. There can be some physics input in it, or some Earth's rotation, Earth's movement towards Sun's movement towards the galaxy. There are several theories on that. Anisotropic inflation. So those are there, but in the CMB, the standard procedure is that you sum over n.
yeah, that's you could say it's an assumption that we are averaging over that additional direction, but yeah, that's based on the isotropic assumption of the universe.
So anyway, this picture is more like a 2-dimensional plane. You are integrating out in radial direction.
Yeah.
So it is basically a plane, and you are taking 2-point correlation on the plane.
Right. Yeah. Yeah, I think now I can proceed to the actual topic of neutrino self-interaction. So I'm also keeping this in mind that this might have some implications or some relation with the so-called Hubble tension, which I'll come back to later. But in the standard model, yeah, as I said, that neutrinos only have weak interaction. So they decouple very early from the thermal bath around the temperature of MEP, and since then they just free stream. They just move at the almost relativistic, so just move at the speed of light and just move through the universe. But what if they have some additional interaction? And for this type of works, we usually assume a very phenomenological effective model of this interaction, a four-frame interaction between neutrinos, which gives a neutrino-neutrino scattering. And you can have some underlying coupling with a mediator mass n phi and coupling g phi. But at the effective level, it boils down to an effective coupling of GF, which we are calling as an analogous to the frame coupling that we have in the standard one. Now, if you look at this plot is redshift versus gamma over H. So this gamma is this interaction rate. So you have a certain cross section and the number density of neutrinos. You can calculate the scattering rate, and you divide that by the Hubble expansion rate. So that's basically tells you if that interaction is strong enough or it's frozen out. So if this number is larger than 1, which means that it's interacting, the neutrinos are interacting. If it's less than 1, which means that they are not. Now, in this orange dashed curve here is for the standard model case. So it is happening around the redshift and before redshift 10 to the 9. But if you allow this interaction, this new interaction, so for these two different examples, you can have this decoupling phase to be almost as late as the matter radiation equality, which happens around 3000, 3000. And of course, in this case, they will stay coupled for long time, for longer after the BBN, and decouple only very late. So this will have implications for CMB.
Is that not remembered in the
So, so the idea of neutrino self-induction is very old, and historically, when people started using the cosmological observations or implications of neutrino, people have been interested in the effective interaction. So this kind of interaction of 4 mediated by some heavy mediator. But there are also some models. Some of them are Myron type models, where you can have you can write down operators like nu1, nu times phi. This phi could be some scalar, and so those kind of models would also give you this kind of interaction. But at the same time, because neutrinos are part of the electron doublets, that might also have some implications for the charged electrons. So you also have to satisfy some constraints from that sector.
This recent work, they can consider this collective excitation for node. You also have the same kind of interaction there, or they do in the quantum mechanical?
I think you can write this same interaction. Yeah. They also have a. No, I'm sorry. So they. So in Basudev's work, they just consider, I think, the weak interaction of standard model. I don't think they have any non-standard. I'm not sure exactly which work, but I don't think in the collective oscillation, right? Yeah, I think that happens even in the standard model of neutrino, because I would naively guess that would even increase the effects of collective oscillations. The collective oscillations become important when neutrinos are you have a very dense environment of neutrinos, either in the early universe or in supernova. And but I'm pretty sure that happens even in standard model. Yeah.
And I'm considering like some nature also like
so yeah, you can have different types of neutrinos here, but this model is very like cosmologically motivated. So we do not consider whether Dirac or if they are Dirac or Majorana. So that. Sorry. In this particular case, it is Dirac, but it's also possible to write down model where neutrino could be a Majorana type. So I'm just not showing that here. So yeah, they are important for different models of neutrino. You could have your favorite model and then write down the interaction. But in the cosmological context, what is really important is only a way for neutrinos to interact. Neutrino and antineutrinos. Yeah. This is the redshift. So it's so the time is going this way. So redshift is decreasing this way. This is increasing time. Yeah. This is late time. This is early time. And so this is the matter radiation equality, and this is the time of BBN, or when neutrinos decouple in standard model, when neutrinos decouple from the thermal path.
You just change does it only change the height of the peaks or also the position of the peaks back and forth, given the fact that they might change this interaction might change the transition time between non-relativistic to non-relativistic?
Oh, you are asking from this floor.
Yeah.
Okay. Yeah. So yeah, I don't think I've gotten this far yet. Let me explain first what's happening here. So if you have this extra self-interaction in the neutrinos, as I said, they will stay coupled for longer time, and as a result, they will not free stream. So, and when they free stream, they erase structure under the length scale of their free streaming. So indirectly, coupled neutrinos will help growth of perturbations, growth of density perturbations. And that shows up in the semi-fast spectrum. So here, the black plotted curve is the lambda CDM1, which is here, and the red one is assume that neutrinos are coupled with a pretty large scattering cross section, and you can see that the red curve is going above the black curve. So it basically says that there is more power or more fluctuations in the universe. Now that's one observation. The other observation is a phase shift. So by phase shift, I mean the position of the peaks. And neutrinos create a phase shift in the semi-fast spectrum towards smaller angles, so larger L's. There is a cute analytical way to understand the phase shift. I'll probably not go. If you are interested, you can ask me. I might have it in a backup slide. But it's also very hard to see here. But if you look at the difference between the curves, you might say it will be easy to see. It also creates a phase shift towards right. So sorry, can you repeat your question again?
My question was regarding this phase shift. Is it happening because the transition of neutrinos between relativistic to non-relativistic phase changes and it contributes to matter instead of radiation? So in the Hubble expansion, the h square, right, or the Hubble radius, so it was earlier contributing to the a to the 4 term, now it is contributing to the a to the 3 term. So is it because of that?
No, it's actually because of the amount of you're changing the amount of free streaming. So actually no, it does not have anything to do with the neutrinos becoming non-relativistic or massive. It has to do with how much radiation or how much free streaming radiation you have in your universe. So there is already a phase in the mass spectrum, right? Even in the standard model. And that phase, you can relate that phase with the amount of free streaming species that you have in your universe.
But that will change the peak height. But do you agree that if I change the neutrino mass,
yeah,
then it will change because it will contribute more to matter,
right,
to radiation.
Right. Yeah. But just by adding, so I'm not changing the neutrino mass here between these two because they have the same mass. What is being changed is only this coupling, and that changes how much of the radiation is free streaming and how much is not. So that's the only difference between these two cases. So, and that's a phase shift that I'm talking about. But of course, if you have a massive neutrino and massless neutrino, there will be another scenario. And of course, there will be something like that.
I mean, the only thing that is, I mean, what I'm not able to understand here is that see what is the position of the peaks, right? The positions of the peaks. Yeah. That is so those are the distance to those modes, right?
Yeah. So it's so the position of
those can be changed with the distance scale, and distance scales can be changed either by background quantities, which omega matter and etc.
Right.
Or some dark energy equation of state.
Yeah.
So peak heights, I understand that that can basically destroy structures and things like that.
Yeah.
But shifting is something that I'm not able to answer. But we can talk about it later.
Yeah. Yeah, as I said, there's an analytical way to understand it. There was a paper by Mashinsky and Celia where they discussed this. There you can clearly see that this phase shift, there could be phase shift for different reasons. So the part of the phase shift that I'm talking about here has to do with the amount of free streaming radiation in the universe. And when you have coupled neutrinos versus uncoupled neutrinos, that changes, the attraction changes, and that gives you this extra phase shift towards large scale. That's basically all I'm saying. Yeah. Sorry. Yeah. So if you compare this curve, the black curve and the red curve, we still have only 3 neutrinos, the 3 times tandem neutrinos, but with extra interaction. No, in this case, we are not changing the mass of the neutrinos. Here,
No, you asked it, but you said.
massless self-interaction. So yeah, I no, we're not changing masses or anything.
Mass is 0.06.
Right, but for this plot, I think we use massless neutrinos, but that doesn't really matter here. You could make this plot with massive neutrino or massless neutrino, and you still see this phase shift. So that's my point. So the phase shift that you see here is just because of this large coupling strength between neutrinos. Sorry, mass. Is there any other question? So I said that it could also be, it has some relation with the Hubble tension. So I'll quickly say what this Hubble tension is, or so-called Hubble tension. So there are two sets of observations or data to measure the H naught. So H naught is a basic parameter in a six parameter lambda CDM paradigm. There are these measurements from the early universe, from CMB and from BBNs, and they give a consistent value of roughly 67.4 kilometer per second per megaparsec. And there is also this other, so that's from the early universe. But there is also this late universe data where people use a distance ladder technique and use CPs or TRGB type of stars to measure this, again, the same parameter, but they get a relatively larger value. So depending on the type of analysis and the particular data set, you could get 74 or 73 point some fraction or one fraction, this number. And depending on the data you take, the discrepancy between this number and this number could be roughly 4 sigma or 5 sigma today. By the way, this particular compilation is a bit older, from 2019. There are more updated ones. There was one in the Snowmass process last year, but this is a less cluttered one. So I'm just using this. So this is called a Hubble tension. So there is this tension between the early universe measurement and the late universe measurement. But at the same point, I should also note this out, that there is one measurement using the tip of the red giant branch stars as a standard candle, and that gives actually intermediate value. So 69.8. This is again from 2019, and this kind of sits in between these two values. So it's still an ongoing debate, and a lot of research has been going on this topic, whether it's actual tension or what's causing this. Now, one solution of this Hubble tension is to add some new physics in the lambda CDM and get a value of H naught from the early universe, which is larger or compatible with the late universe data. So one model is this neutrino self-interaction. So this was done in a few of these papers here, and this I already mentioned, that the effect of adding neutrino self-interaction is to increase the amplitudes of the CME power spectrum and also make a phase shift towards right. And you could also, so that already gives you a bit larger value of Hubble because of the degeneracy between this new coupling and Hubble, but you could also add more neutrinos. So that's this parameter ineffective. So ineffective is basically, it tells you how many thermal species are there in the universe. So typically in the standard model, this number would be 3.046 because of 3 flavors of neutrinos. But you can also treat that as a free parameter, and you can vary that. And that actually cancels some of the effects of this neutrino self-interaction. It actually decreases the amplitude and also makes a phase shift towards the left. This again has to do with the amount of free streaming species that you have in your model. So, and both of these parameters have the same degeneracy with the Hubble. So both of them actually try to increase Hubble. So they showed that if you do that in such a model and use the Planck data, you can get a relatively larger value of this neutrino self interaction and also increase the value of Hubble. I mean, of course, yeah, it increases, but it probably doesn't go all the way to the value that you would love to 73 or 74, but around 70. But this was publicized very well, very widely, and it was kind of shown that it actually, yeah, we could solve the Hubble tension.
But it is with the DT only, but if you had any polarization, maybe it's down to 65.
Right, exactly. So the point in their paper was that they were using the Planck 2015 paper, and they probably it was correct for them to do is that there was some systematic problem in the Planck polarization data in 2015. So they did not include the polarization data for this data set, but they
Last year there was that we did not use the last year, but still didn't change much.
yeah, but that was their argument, and
Has there been any update on this?
yeah, that's exactly my next slide here. So we updated that with our work. This I did with my another postdoc in Notre Dame University, Shoji. So there we actually use the full data set of from 2018 and temperature and electron polarization data. And now you can see that this strong interaction mode. So you actually get in the posterior, you get two modes. So one is this small coupling, which is basically like lambda CDF, so no interaction. And there's this higher mode, higher coupling mode. But if you use the Planck polarization data, this higher interaction mode actually gets killed out. So and you could also see this in the 2D parameter space of coupling and H naught. If you look at this red contour, of course you still get this mode, but the significance of this mode is much smaller than this lambda CDF mode. So it basically tells you the Planck polarization data is telling you that there is strong neutrino self interaction is not possible.
That 69.5, that is not, that seems to be for that mode.
Yeah.
Seems to be for the left part, it is nearly 2 sigma out, right? If I look at the red one,
Yeah.
it's actually out, then it is 69.5 is at the top, right?
Yeah. So this number is for this mode.
Okay, so you have not considered, you have cut out
Yeah,
that
I
part,
cut out this part. Yeah.
and then you have taken the average, the posterior V,
Yeah.
posterior V.
Right. Yeah. And that gives So this is that's tying. We are just trying.
Right, right.
No,
You have a
yeah.
bimodal distribution. I understand that there may be
Yeah.
tension, but you cannot just
Right.
take one part out where the most of the probability.
Yeah,
is
exactly. So yeah, so this is just for my talk. So I'm not in my paper. If you go back to my paper, you will not see me as or we as advertising that this is the solution. So this is the number you should.
No, no, you can even say that it actually increases, but cutting that and saying this is the number, this is something that I am objecting. I mean, it is, you can say that it increases, but no numbers will be given. So if I have a probability distribution, I can simply say x fx dx integration that gives me the mean. Right?
Yeah,
It
so-
doesn't matter
so-
whether it is bimodal or anything.
So yes. So exactly. I mean, when you do the data analysis with this bimodal posterior, you actually have two modes, right? You actually separate this mode and this mode. So in our paper, in our tables, we actually show the two values, one for this mode and one for this mode. And we also show that what is the significance, the relative significance of the modes, and they are of course this mode objects. That we clearly say, and never ever we say that this is a solution of our picture. This just to show that how far you can actually get with this type of model, this type of scenario. But because people are interested in this, and the other thing is that you have been seeing this symbol here. This basically means that all three flavors of neutrino have the similar interaction. So it's called we're just calling it three couples 0 3. But that's not the everything. So there are, as I think I mentioned in one of the answers to the questions, this universal coupling of neutrinos is very, very highly constrained by other laboratory experiments. So if you go back to your model of this interaction, and this is the mediator mass, and this is the coupling for that mediator, and there are constraints from, like, of course, there is a constraint from VBA. If the mediator is very light, it will thermalize and it is ineffective. But there is also this other lab constraints from meson decays and other neutrinoise double beta decays. So you see these bands where this neutrino sulfate interaction is important. They are completely ruled out today. But what is still possible is that only one of your neutrinos is interacting. Maybe one or two are interacting, and in this case, there's still, even if it's marginal, but still there might be some parameter space still open. So that's what we also did in the same paper. So we consider these other two scenarios. So only two are interacting, or one is interacting, and these are the other contours here. So blue one is for two neutrinos, and the green one is single neutrino. Now, one thing that you see, that lambda CDM mode is basically the same for all of them, but for the high interaction mode, or strongly interacting mode, it's actually coming down towards smaller Hubble. And this is happening because if you go from 3C to 1C, you are basically decreasing the amount of neutrinos or number of neutrinos interacting. So that basically decreases the effect of neutrino sulfate interaction, and proportionally that also decreases the value of Hubble. So it actually goes down. Although the significance of the mode increases, but it's not really a solution. But that's not the end of the story. So in this recent paper earlier this year, we updated this result again using the data from ACT. So ACT is another CMB telescope. This one is ground-based. Atacama Cosmology Telescope. It's in a Chilean desert, Atacama. The difference from this telescope with the Planck is that it has a much better resolution compared to Planck, so it can actually measure much smaller angular scales towards the right of the CMB power spectrum. And we did this analysis with the ACT only data. So this is only the ACT. And if you look at this top left plot again, this is the one posterior of this same coupling. Now you see that there is a huge boost of to these strongly interacting modes. This sits very in stark contrast with the Planck data that I showed earlier. It basically gets killed this mode, but in this case it's hugely boosted.
This is just ACT.
Just ACT, and we also use some tau prior for low L data, because ACT does not have any data for low L's. So, but this is what we get. This actually has actually favors the strongly interacting. We also looked at the data very carefully. Why this is happening? It's happening right now because there is a mismatch in the data between the Planck and ACT in the L range of roughly between 1500 and 2000 for temperature, and in roughly 600 to 1000 for polarization. And right now we think
they prefer two different NS values.
NS. Oh yeah, right. Yeah.
They prefer two different NS values. There is a tension.
Yeah, exactly.
That's what you are picking up in this one.
Yeah.
But what I am basically not able to understand that when you have this one is one neutrino has this interaction and two are this standard ones. Then your NS goes much higher. Oh, okay. Then it becomes as close as okay. So it helps in reducing the tension. You understand what is happening here? Look at the top, bottom right one.
Right. Yeah.
No, bottom right.
Oh, okay.
Yeah. See, when you have 0C, okay, 0C plus 3F, then it should be as good as the lambda CDM baseline. So, which prefers NS value of 1.0 close to.
Yeah.
As you have more self interactions, okay, then your thing comes closer to the Planck. So this actually seems to be solving the Planck and ACT discrepancy.
But if you take the G effective into account, then it doesn't really helping to solve the tension, right?
You see the red uh, PDF. One dimension. So right now,
Okay. Yeah.
it peaks at 0.96. 0.96 or 0.97. Whereas the baseline model actually is basically that close to the baseline model, 1C wave is around 1. That is the famous discrepancy between Planck and SCP. But if you have more self-interacting neutrinos, it is solving the discrepancy. That is what I'm saying. Your model helps in solving the discrepancy. Of course, it might have other things, but it may be something that is of interest. Okay, I can talk to you about it later, so you can proceed.
Okay.
Probably you can go a little bit fast.
Okay,
There has been lots of discussion, but it is good.
Yeah, sure, I'll try. So there's this apparent mismatch right now, but we think that this is just a statistical fluctuation at this point between the data of Planck and SCT. Okay, so that was about self-interacting neutrino in the early universe, but there are other neutrino sources in the late universe. So this is a rank plot of all different types of neutrinos. So this is a cosmological neutrino that has been there since the Big Bang that I talked about, and they are very low energy right now. This is called cosmic neutrino background. But there are also other neutrinos like solar neutrinos from the Copula supernova, and this background old supernova. This is basically neutrinos from all the supernova in the high redshift. There is atmospheric neutrinos, and there are high energy neutrinos. So it's also possible then that different components of these neutrinos can also talk to each other and have some observable signature. So one of these sources that I'll highlight here because of my work is the DSNB or diffuse supernova neutrino background. As I was saying that there are these Copula types of supernova which dumps a lot of neutrinos in the universe, and they have been happening over many years and over a long range of redshifts, starting from the redshift of roughly 5 or 6. And by today, there has been a huge flux of an isotopic flux of neutrinos in the universe. This is called diffuse supernova neutrino background. You can calculate the theoretical flux of that. If you know the star formation rate, you can tell how many supernova were there, and you know the neutrino flux from the individual supernova. So then you can just integrate over the redshift and get the flux. And there are experiments that are coming up to detect this DSNB. So Super K is a very old experiment, but recently they are loading their detector with gadolinium, which helps to which will help to detect the DSNB, and hopefully this will happen within perhaps 6 or 7 years. But there is also experimental endeavors going on to detect the cosmic neutrino background. So this is a very challenging experiment. We are talking about neutrinos of energy of milli-electron volt or tens of milli-electron volt. And there are ideas, they have built a prototype, but there's still a long way to go here to actually detect the cosmic neutrino background. But still, there is experimental activities here. So what we asked is that what if this DSNB, which has been coming from this late redshift, what if it interacts with one of these cosmic neutrino background and changes the spectrum of these neutrinos? So we calculated, we know the fluxes of both these neutrinos, then we calculated the expected rate, neutrino interaction rate in some of the detectors. So we used a proposal, a new type of detector, ResNova, where they will look for 7-stack neutrinos. So that's like a coherent interaction between neutrino and the whole of the nucleus in your detector. But right now we see this, so these are the plots for different coupling strength. This is again GS is the same coupling that I told you before. But looks like right now most of these rates would be subdued by the background from solar and atmospheric neutrinos. So even though it is an interesting idea, but it will be very hard to see them in future experiments. So this is a work that I did with two of my postdoc friends, Uber and Monica. So finally, before leaving the picture of neutrino self-interaction, I wanted to show you this landscape, the whole landscape of this parameter space. This is again the mediator mass, and this is the mediator and neutrino coupling. So you see this CMB constraint here, which I showed before, it's sitting right now here. Because it's not the most constraining one, and there are also other the constraints from DVA, double beta decay, and meson decays. There are of course some experiments which are coming up and which will explore more of this parameter space. And a good benchmark in this parameter space is this solid solid black line, which basically says along this line neutrino could be darker. So it's like a goal post that we are trying to reach. And this is taken from the our white paper last year from the Snowmass process. Now, the second part, I'm not sure how much time.
I think that we are already nearly 15 minutes overshooting the time.
Okay.
There has been question answers about 15 minutes, but I think you should wrap up pretty soon.
Okay.
How long do you think this can take?
Maybe another 6 or 7 minutes.
Okay, 6 or 7 minutes.
Tomorrow that would be a different topic. I'm sorry about this. I should have started with it.
But anyway, please.
Yeah. So now to go into the direction of neutrino dark matter connection, one interesting idea is the boosted dark matter. But I want to explain why we need boosted dark matter. So boosted dark matter means that something is giving extra energy to dark matter today. So dark matter today is non-relativistic, as we know. But there could be some non-standard interaction, which is some high energy particles, so the electrons or protons or neutrino with dark matter, and that can scatter with them and accelerate them to higher energies. Similarly, if some dark sector particle annihilates or decays into dark matter particles today, that can also create high energy, relativistic or semi-relativistic type of dark matter. So this is interesting because this gives us chance to probe lighter dark matter, which are usually below the experimental threshold in some of the direct detection experiments. So this gives us high energy dark matter, so you can probe them in experiments. But the penalty is that you have to have two scatterings. So you have to boost them first or create them first and then detect. And it's of course a very active field, and lots of papers are being written here. And these are some a bit older plots on this idea of boosted dark matter. So you can see that compared to these usual direct detection experiments, these constraints are sitting to the left of the parameters dark matter parameter space. So we are probing lighter dark matter. So our idea was to use again this same DSNB population of neutrinos to boost dark matter in the Milky Way halo. So the same neutrinos, they have the energy of typically MeV or tens of MeV, and they can come and scatter with the dark matter, and then that can boost it towards the Earth. This is a work that I did my friend with Monica, and we call it SNB. There are of course there are models, but I'm not gonna go into the details. So you can see that we calculated the boosted dark matter flux. So this is the dark matter kinetic energy, and this is the flux. If you compare with the standard halo dark matter population, which has this kind of distribution, so it's highly boosted. You can go for a 300 mega electron volt mass. You can see that you can have really boosted dark matter from scattering with DSNB. And we looked at initially we looked at only the xenon experiment, the xenon one-ton experiment, the result of which came out in early 2020. But there are also other experiments, low threshold neutrino experiments like Boixino or microboom, where this can have observable signatures. So in that paper, we got this limit on the dark matter electron scattering cross section as a function of dark matter mass. So it's so you can see that it's although the data here was relatively poor, but we still got some nice constraints out of that. But there's still more of this parameter space to the light and dark matter to the probe. Actually, I'll talk more about light dark matter tomorrow. And right now we are trying to use the new data, better data, where they don't have any excesses or anything, and they understand the background very well with the xenon n-ton. And we are right now trying to use this data to update our constraints. And actually, it turns out that we can actually do at least a few orders of that better than the previous one. Finally, this is another nice work that I did with Shiv and Shubinoy, is that we try to explore a new type of dark matter model, which kind of bridges the gap between the ineffective and warm dark matter. So warm dark matter is like massive neutrinos. So they were there relativistic initially, but at some point they became non-relativistic and became dark matter. So that's a warm dark matter. There is also ineffective, in which case you have some extra radiation and which remains radiation or remains massless throughout the history. What we asked is that what if the mass of this particle or mass of the dark matter has some time variation? And there are a few models where this can happen, and we call this a mass varying dark matter. But for our work, we just took a very phenomenological approach and took them. We modeled the time variation of mass with this tan hyperbolic function, and so you see that the background density, the energy density of the species will look like this. It will be like radiation, and then it will transition to a matter-like variation. And the results that we got in the power spectrum is that it basically qualitatively it looks very similar to the warm dark matter case. So it has a suppression at the small scales, but you have opened up the parameter space, so you can tune the point when this transition is happening. You could also set the speed of the transition differently, so you can have a slow transition or fast transition. And in this whole parameter space, now you have the mass of the dark matter and also the transition time, CT. We use the linear alpha data, the latest one, and we got some constraint which is a bit smaller, a bit stronger than the delta input constant that we had in this parameter space. So this was another result that the theory that I worked on. In future, I have a very observational motivated or experiment motivated approach. I want to go where the data is coming from. So we have multiple CMB experiments that are coming up. So CMBS4, probably core also will happen, then and the Lightbird by the Japanese Aerospace Agency. And some of them will give us more data in the lower angular space, lower angular scales, and also very much better polarization data. So I'm planning to use this data for in a broader sense, also in neutrino self-interaction models and also in other dark sector models. And JWST is already up and taking data, and so it has already given us some interesting ideas and interesting observations. And I also want to use test some of the theories with the data coming from the JWST. And finally, 21 centimeter is a front, I think, where India has very much potential, and there are multiple experiments going on. Sapsara in India, in this area, and there's an idea of Pratush to send a probe on the far side of the moon to make measurements in the 21 centimeter data. So this can also will also give us handle in the small scale data, small scales structure formation. The other thing is in the direction of neutrino dark matter phenomenology is that, of course, we are going to use the future data coming from the xenon n-ton, and also there's the idea of Darwin, where hopefully the Lux collaboration and the xenon collaboration will probably get merged, and probably they will build a bigger detector, and that will increase our sensitivity by many orders of magnitude. So these are some of the ideas that I'm planning to my 5 or 6 years of future plan. And here the collaboration, my collaborators and my research funding. And finally, I think I'm not going to go through the details. There's summary here you can read. And thank you very much for your attention. And if you have any other questions, we have to answer.
Yeah, so thanks for the nice talk. So I don't, like, I'm not an expert in this field, but like, does your boosted dark matter by any chance like explain the electron recoil excess that was seen in the xenon 1G?
Yeah, right.
What kind of models are you using to explain that?
Yeah, so in our work, we assumed a leptophilic type model of dark matter. So dark matter talks exclusively with the leptons, both electrons and neutrinos. It actually helps us because we are boosting the dark matter using the neutrinos. So you need to have a neutrino coupling, and also in the detector you have electrons. So you have to talk to the neutrino and electrons. So that kind of model works very well. So that's the type of model we use. But actually in the work we were very model agnostic. We did not specify that type of model or anything. We just took the scattering cross section as a feedback. Yeah, and yeah.
So last. I don't know where the hot model is, but you described this H0 cancel, and what I understand H0 cancel there is a value which range from 50 to 75 and we don't know why it is moving. Probably the method of the reason we are people are using. I think you are trying to explain it's not and why need to know interaction.
Yeah.
So my conclusion is like that's not problem arises people doing some different methods to calculate the value or data.
So we right.
Right.
Yeah, so we don't know the answer to the tension, right? So there are this early universe observation, late universe observations. Now we don't know which one is correct. So the two ways to go about this, like to solve the tension, is either you can do something in the early universe, you change your lambda CTM and get a value from the early universe which moves the value of H0 to closer to the late universe data, or you could do something in the late universe and say that decreases the value of the late universe data. So that's only if you want to add some new features. But of course, it's always possible that we are missing some systematics in one of the observations, and maybe in the late universe observation there is some systematics in the speeds, the magnitude, and the brightness calibration, and something is we don't understand that very well. So that's always a possibility. But yeah. Does that answer your question?
Okay, then. So you will be here till 11, right? 11
I'll be here for the
and you have been given an office, right?
yeah, I'm sitting in 104.
Okay, so if you have any questions you want to discuss with me, please talk to me in 104. And if there are no further questions, thank you.
Oh, there were three.
Just a quick question. So, I long back I had done a project on neutrinos and dark matter, but the idea was that the idea of dark matter is not very compatible with the idea of structure formation, right? Like, so if you consider your dark matter models to be bound dark matters, then the structure formation has some issues. The way we know it. So how compatible are they?
Why do you say that it's not compatible? Because it has suppression at the small scale.
Right. Like
Yeah,
that's
but
not the reason. And then like so the scales that you require for this structure formation to happen, you require that the dark matter mass be certain range and it has certain velocity.
So that gives you an lower limit on the dark matter mass. So you cannot keep decreasing the dark matter mass.
Correct. So that rules out the warm dark matter theory. Right?
Not really rules out. You could say that the current limit is sitting at a few K, like 3 K or 4 K.
But
So
certainly the neutrino mass is supposed to be more less than the kiloelectron volt.
Yeah, so neutrinos cannot be dark matter. The standard model neutrinos cannot be dark matter at all. So that has been ruled out long time ago.
So you're considering some other species of
Right.
neutrinos
It could
which
be
can
sterile
get,
neutrino.
right.
So that's a new DSM neutrino. Correct. That could be dark matter. That's still possible. And the mass of the sterile neutrino could not be less than a few kV.
But then, again, I have a very naive understanding of these things, but the idea of sterile neutrinos poses some issues with the observed ratio of the baryons to photon, right? That has some issues if you consider another species of neutrinos.
You mean the ineffective constraint that you have extra radiation?
There is a well-known this ratio of the number of baryons to the number of photons.
Yeah, 10 to the 9. Sorry,
Correct.
baryon over photons, so 10 to the minus 9.
Yeah, so that ratio gets affected if you consider another species of the neutrinos, right? If I'm not wrong.
It will change.
So the current value that we have based on the three neutrino species, that is in agreement with what is being observed from CMB as well.
Yeah,
So how do you explain this, like including another species of neutrinos?
Yeah. Right. So remember, what's important in the CMB is a parameter called ineffective. So ineffective is basically the amount of radiation relative to the thermal species. So you can have a species which is not very hot or does not have high temperature, so that the energy density is low. So you can always have that as a dark radiation or an additional species, but will not contribute substantially to the ineffective. So you can have a small amount of delta ineffective, but you're still fine. So yeah, but of course, right now the measurement, I think the latest Planck measurement of delta ineffective is around 2.98 plus minus 0.1 or some 0.2.
Right, and that's not really in contradiction. It's not in conflict with adding another species of. Like if you do a theoretical calculation by adding.
If you just add another EV mass neutrino, that is ruled out. That cannot happen.
Yeah.
You have to add a heavier mass.
I see. And sterile are supposed to be heavy.
Yeah, sterile is yeah. So KV sterile neutrino is also theoretically interesting. Also cosmologically viable. So that's a more interesting thing. So people have talked about EV scale sterile neutrino for other reasons. So there are some excesses seen in the short baseline neutrino experiments. But if you to do the cosmology with EV scale neutrino is not possible. That kind of rule out. There's also a new result from microbore which does not see any excess. So nobody knows what's going on there. But KV sterile neutrino is still allowed.
Excellent.
Thank you. Yeah, are you a student here?
I'm a PhD student here. I work on mainly quantum gravity aspects like holography and those kinds of things. Previously, I had worked on neutrinos and dark matter.
Oh, okay. Like in your masters.
Yeah, summer projects actually. Nice to work. Yeah, so for neutrinos, I worked on a neutrino oscillation with Poonam Mehta from JNU.
Yeah.
And on dark matter, I was mainly working on the next direct reading projects at HRM with Vishwarup Kupante.
Oh, okay.
It's mainly reading projects.
Okay.
My masters.